Okay. Let's knock this one out so we can get on to waters of constitution and hydration lab. All right, number 2. Let's see. What's the kinetic energy of a 1.56 kilogram object moving at 94 kilometers per hour? So what we've got, we're looking for kinetic energy, right? We've got the mass of an object at 1.56 kilogram. Yeah, and 94 kilometers per hour. 94 kilometers per hour. So what's the formula? Remember? 1/2 mv squared. That should be in your useful information on the last pages of the review document. And in order for the kinetic energy to come out in units of energy, which would be joules, mass has to be in kilograms, and velocity has to be in meters per second. That's good. That's kilograms. This one's not. We have to change this one. So we need a little dimensional analysis. Let's change the kilometers first to meters. How many meters in a kilometer? 1,000.
Oh, yeah.
Yeah, 1,000. Okay, take care of that one. How about, then we're going to do hours. Hours is in the denominator, so we have to put hours here. Hours here. And we need to be seconds. Right, how many seconds in an hour?
3,000 something.
60 times 60.
Yeah.
3,600. There we go. So that should give us the velocity in SI units. 94 times 1,000 and divided by 3,600. Should be 26.1 meters per second. Now we can plug them into the formula. 1/2, 1.56 kilograms, and then meters per second, 26.1 meters per second. That's squared. Okay. So we'll go ahead and square this value right here. And 1.56 times that divided by 2. So I get rounded off to 3 significant figures. 532 joules. Oh, it's in scientific notation. 5.32 times 10 to the 2 joules. It's in the kilojoules. It's in kilojoules. Okay. So let's do it this way. If the units get bigger, the number gets smaller. All right, so we have to move 3 to the left. Let's see. 1. Okay. 1, 2, 3. There we go. Joules, then kilojoules, we would kilojoules is going to get bigger. Oh, all we have to do now is say, what does kilo mean? Kilo means 1,000. All right. So if kilo means 1,000, we need 1,000 times that. Actually, we already did that. I'm sorry, we already did that. Now we can say 5.32 times 10 to the minus 3 kilojoules. No, minus 1. What did I do wrong?
Cause it's, if like a kilojoule is 1,000 and we have 532 joules, will that be like 0.532 of the joule? Or
Yes, exactly right. And then you can put that in scientific notation. I was making it harder than it need to be. Okay. Number 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process at 1 atmosphere pressure and 370 K? So they're saying the pressure is going to be constant at 1 atmosphere and the temperature equals 370 K. There we go. And the process is condensation of steam. Okay. This happens at, let's see, 370 K is pretty close to the boiling point. The 273 plus 100 is 373. It should be 373 would be at the boiling point for 1 atmosphere. I think that's what they were getting at. But if we're going to determine the value of Q and W, I like to draw pictures. All right, if we have a piston in here, and we're going from gaseous water, going from a gas to a liquid. So the problem tells you it's exothermic. It's got to give up heat. So that means this is going to be negative, right? We know that right off. How about the work? If this is the system right here, and the gas condenses to a liquid under a constant pressure, what's going to happen to that piston? It's going to go down, right? That means we're doing work on the gas. So that means this has to be positive. Okay. So C is the answer. Negative, positive. All right. Number 7. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atmosphere. How much work is performed on the surroundings? Okay, 1 mole of ideal gas is expanded. So it starts here and it ends up here. Right, it's going that direction. Against a constant pressure of 1 atmosphere. Okay. And it goes from a volume of 1 liter to 8.93 liters. So it's not to scale. This is 1 liter, and this is total of 8.93 liters. Okay, so if we're going to calculate the amount of work that is performed on the surroundings, that makes sense because as the gas expands, it's doing work on its surroundings, right? So what's the formula for that? Work equals negative P delta V, right? P is constant at 1 atmosphere. So when we see a delta That's final minus initial. So the final is 8.93 minus initial, right? And the pressure is 1 atmosphere, and we have the negative sign there. So this is in units of liter atmospheres, which would be 7.93 minus 7.93 liter atmospheres. But our answer is in joules. So we need a conversion, liter atmospheres to joules. Let me make some room here so I can do the conversion. All right, so we need, and it's in the problem, 1 atmosphere is 101.3 joules. Like that. (7.93) 101.3. And I get negative 8.03 times 10 squared joules. Oh. There. Now, if we're paying attention to the sign, it should be negative. Yeah. Right. About 12. Calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure of 13.1. And this is in liter atmosphere, so this is even a simpler calculation than the one before. So the work is equal to negative, and the pressure is 13.1 atmosphere. And the change in volume is final minus initial. So it's going from 121 to 80. 80 is final minus 121.0 liters. Okay. So we're going to end up with a positive value. Does that make sense? It's going from 121 to 80. Yeah. We're compressing the gas. 13.1, I'll stick that one in there. And then 80 minus 121, and then times that one is 537. Is it standard units? Yeah. 537 liter atmospheres. And that's positive value. Okay, the next 14, 15, 16, 17. Yeah, I think it goes through 17. 14 through 17, based upon that first paragraph. Okay. The true value, okay, we got Q, W, delta E, and delta H. Q, W, delta E, delta H. There we go. Okay, so based upon this paragraph, a 1 liter bulb at STP is connected at standard temperature and pressure. Is connected via a valve to, get this out of my way, it won't move. There. Initially evacuated. Okay, so a 1 liter bulb is connected via a valve to another one, and we don't know how big this one is, but it doesn't matter. That's a vacuum. And this is 1 liter. Okay. Okay. We want to know what what are these values, relatively speaking, when we open that valve? We know what's going to happen, right? That air is going to rush over here. The gas is going to rush over there until it's the same pressure throughout. So what about the value of Q? Well, if it's all at standard temperature and pressure, right, 1 atmosphere, and let's see, for gases, it's 0 degrees C. That doesn't change. Q is a measurement of transfer of heat from one place to another. If the temperature didn't change, there's no transfer of heat. Right? And if the pressure is constant, the enthalpy is also 0. Right? Okay. So how about work? Was any work done? No, it wasn't pushing against anything. It just moved and filled the space. There was no work done at all. And delta E equals Q plus W, right? So 0 plus 0 is 0. For this situation, all of those values are 0. Right? Now we're going to find out why that happened, because something had to make it happen. But these values can't be blamed for moving that gas. That comes next semester. We talk about entropy. Just a little teaser. I'm sure you're all excited to learn about entropy. All right, so now we're down to 18. Energy, work, enthalpy. Okay, I forgot and left them bolded. So you got the answer there already. How many are state functions? Energy, work, enthalpy, and heat. Energy, work, enthalpy, and heat. These you usually have it like that. Which are state functions? That's a state function. That's a state function. These are both path functions, which simply means that all you need to know for this one is the conditions. Doesn't matter how it got there. Or you know beginning and ending, and whatever happens in between doesn't matter. Whereas work and Q and heat, it does matter the path that was taken to get there. Okay, so the answer's 2. Only 2 of them are state functions. 19. Which of the following properties is or are intensive properties? Remember the difference between intensive and extensive properties. Extensive property changes its value with the amount of substance. So mass would be extensive. Temperature is uniform throughout, no matter how much of the substance you have. So temperature is intensive. That's one of them. Volume changes with the amount of substance. Concentration is uniform throughout a solution. So that one is also intensive, and energy varies with the amount of substance. So you only have 2. C, 2 and 4 are intensive properties. Most intensive properties have units of measure that are ratio. 2 units in ratio somehow. Temperature is unique because temperature is an expression of average kinetic energy of all the molecules in the substance. How about 23? Consider the reaction. Ethanol plus oxygen yields carbon dioxide and water with a negative delta H. So it's exothermic, which means it's Roman numeral 2, We know it's exothermic because it has a negative delta H. What else? It can't be endothermic. The enthalpy term would be different if the water form was gaseous. That is true. If the water term were gas, then some of that energy would be used up in taking the liquid to a gas, and the enthalpy would be a smaller value, a lower value. Okay, so number 3 is also true. 2 and 3 are true. So that means E is the best answer for that one. When we're just balancing equations, usually the state doesn't matter. But in many cases, the state does matter, and this is one of them. Okay, how much heat is required to raise the temperature of 5.75 gram sample of iron from 25 to 79.8? This is 24. Okay. What are we given? A sample of iron, 5.75 grams. Grams of iron. And we have an initial temperature of 25. And a final temperature of 79.8. We're also given the specific heat of iron, 0.450, 0.450 joules per gram degree C. Okay, what formula do we need to solve this problem? U equals specific heat times mass times delta T. Okay. Let's see. Grams here. This constant tells you the value, the units of measure for the others. Grams, grams. Degree C, degree C. And then you're left with joules. So we're good to go. We just have to plug the values in. And I'm going to leave the units out just for brevity. Final minus initial. Oh, and mass. Left the mass out, sorry. 5.75 grams. There we go. And if we do our math right, it should come out to 142 joules. Just to save time. Okay. Now, if we had, if we said it takes 142 joules to raise the temperature of iron, 5.75 grams of iron from 25 to 79.8 degrees, what's the specific heat? That leaves us with one unknown. We can solve it. Like any equation. Only one unknown, it's solvable. Okay, 26. 32.5 gram piece of aluminum with a molar heat capacity is heated to 82.4 degrees and dropped into a calorimeter containing water. Initially at 22.3 degrees. Final temperature of the water is 24.2. What was the mass of the water? Okay. Let's put what we know up there. 32.5 gram piece of aluminum. Mass of aluminum. 32.5 grams. Molar heat capacity is 24.03. Molar heat capacity equals 24.03. Joules per mole degree C. Okay. There you can see a fly in the ointment already. That's not in moles. So we're going to have to convert that to moles in order to use this value. Let's see, what else are we given? The initial heat of the aluminum, temperature of aluminum is 80, getting the glare. 82.4. Okay. Then we have water, and notice we're ignoring the calorimeter. In real world, you can't do that. But we're saying the calorimeter contributes nothing. It doesn't remove heat, doesn't add heat. Initially, the water is 22.3 degrees. So the initial temperature of water is 22.3 degrees C. The final temperature, which is the final temperature for both of them, because now they're together in the calorimeter, is 24.2 degrees. Okay. And then the specific heat of water is the same as it's always been, 4.184, is it? Just 1.8. Sometimes we get a third digit out there. Joules per gram 3C. All right, we know we're going to have to convert this to moles in order to use that, so we might as well do it now. All right, what's the molar mass of aluminum? I can't read it from here. Aluminum, 26.98. Almost 27. Okay. So we just need to divide that into 32.5. And I get 1.205 moles. Okay. Now we have to set up the problem. Remember, calorimeters are isolated systems. They're even isolated from their surroundings. So an isolated system says that everything that happens in that calorimeter in terms of heat has to be 0. So we've got a Q factor for the aluminum and a heat factor also for the water. Right? Now, I should have put that up higher. That's okay. Now, what's the Q for aluminum? Well, the S for aluminum is 24.03 joules per mole, 3C. And moles of aluminum is 205. And then delta T for aluminum, final minus initial, 24.2 minus 82.4. Okay? That's for the aluminum. Now for the water, we have, let's see, 4.18. I'm gonna leave the units out for, because I'm running out of room. And the mass of water is unknown. That was the question. And delta T for water would be 24.2 minus 22.3. There you go. All the thinking's been done. The rest is number crunching. So how do we crunch these numbers efficiently? Well, number, we can do this whole thing right here as one answer. 24.2 minus 82.4 times 1.205 times 24.03. And this gives us 0 equals a negative 1685. And that's moles, degrees. This is joules. Okay. Now what's inside of this one? Well, we got a number here and a number here. So we can take 24.2 minus 22.3. Yeah. Can't read my own handwriting. So that's 1.9 times 4.18. And this is 7.942 times the mass of water. All right. Now what do? We get all our number terms on one side and our unknowns on the other side. That means this one comes over here as a positive. And then we have 7.942 times the mass of water. So the mass of water is that looks like a 5, that's a joules. 1685. 1685 divided by 7.942. So the mass of the water equals 212 grams. Ordered that. Yeah, it asks for mass, 212. So that's A. Okay. These calorimetry problems, you have to be extremely methodical about setting them up. Follow the pattern, set them up correctly, and then be careful when you're doing the calculations. That's the voice of experience. All right. You can make just one tiny mistake and it'll just throw your numbers way off. That's why I spent so much time on that one. I think we have a calorimetry lab comes later, doesn't it? Yeah, it comes on the 25th of October. We skip next week for lab, and so I'll give you the lab next week. And the week after that is when we do the calorimetry lab, based on this stuff right here. Okay, 27. .9 sample of metal is heated to 95.2 degrees, then placed in a calorimeter containing 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. What metal was used? And this is based upon the specific heat of the metal. All right. So I'm going to try to do this without slapping it up on the board. We know that our calorimeter, whatever happens in Vegas stays in Vegas. So we have a Q of the metal, which we don't know what it is right now. And then we have the Q of the water. And again, they're ignoring the calorimeter. So the Q of the metal is equal to the specific heat of the metal times its mass. The specific heat is the unknown. Times its mass, which is 45.9 grams, and then delta T. So the final temperature is 24.5 degrees. And the initial temperature was 95.2 degrees for this metal. Okay. So that's this term. And then we have the term for water, 4.18. And yes. The mass of the water, which was 120. And then the change in temperature. The final temperature is the same. The initial temperature is different, 21.6. Okay, so now we've set that problem up. We can solve this for a number. We can solve this part for a number. Then this one, change the sign, goes on that side, and this part divides into it, and that gives us S. Okay. And it should come out close to 0.45 joules per gram degree C, and that means it's iron. Okay, I'm just trying to save time. Otherwise, I'm going to run out of time. I don't want to eat into our lab. All right, 28. You take 295.5 grams of solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. Okay. I don't think we talked about heat of fusion in the video, of course. But the heat of fusion, Q of fusion, is simply the amount of heat let's say it's not specific heat. It's let's give it a C. It's a constant value for any substance to go from solid to liquid. Okay, fusion is the other way, from liquid to solid, but it's the same amount of heat. It's just flip the signs. So the heat of fusion is going to be some value here with units of measure, joules per gram. Because when you melt something, the temperature doesn't change. Right? That's why I insisted that if you wanted to know the freezing point of water in our previous lab, you got to be sure you have solid ice and water together. As long as they're both there together, temperature doesn't change. So we don't need a temperature term for this one. This is some value here. And if we know the mass of the substance, this is the this is the heat of fusion. This is the total heat. This is the heat of fusion. So if M is 295.5 grams, and this is our unknown, and the heat that is given up and absorbed by the water is the other term. This amount of heat given up by that solid is absorbed by the water. And the water is 4.18 times the mass of the water, which is 425 grams. Right? And then it's change of temperature. Right? The water temperature decreased from 85.1 to 30. So it went 30 was the final minus 85.1. There we go. Now we got it set up. So let's solve this side over here first. All right, this is minus 97885. 1, 2, 3, 4. That's right. Joules. And that means that if we want to find that value, we divide this one by 295.5 joules per gram. Joules. 331 joules per gram. Now the heat of fusion, it just depends on which way you're going. Are you melting it or are you allowing it to solidify? In this case, we're melting it. So the value should be positive. We got a negative here, but that's only because of the way we set up the problem. The value is 331 joules per gram. Okay. $32. In the lab, you mix two solutions, each originally at the same temperature, and the temperature of the resulting solution decreases. Okay. If that happens, what we've witnessed is an endothermic process. It's just like those cold packs that you get at the hospital. You break the capsule inside the bag and dissolve the substance, it gets cold. So which of the following is true? If we mix these two together and the temperature decreases, the chemical reaction is releasing energy? No, it's absorbing energy. So C would be a valid answer. It's absorbing energy. Energy released is equal to Sm delta T. Well, it's not releasing energy, right? That's the key word there. It's not releasing energy. So it doesn't matter Sm delta T, it's not releasing, so B can't be it either. A and B are false. The chemical reaction is exothermic? Nope. And there's not more than one, it's just C. C is the only one that fits those conditions. All right. I think they use ammonium phosphate in those capsules. I think
They
they
usually give you at school if you like hurt your arm or something.
yeah, same thing. And then there's another one that gets hot when you mix it.
Oh, you talking about like things, hand warmers? You like?
No, that's different. Yeah, that's a supersaturated solution, and all you have to do is it's got a little clicker in it, and that starts it. Once it goes from solution to a solid, then when you go from individual ions down to a solid, that's lower energy, so it gives up heat. But if you stick it in boiling water, then it'll redissolve and you're ready to go again. Now, this is heat of solution. If you take a solid and dissolve it in water, sometimes it gets hot, sometimes it gets cold. And there's no way to tell, except experimentally, which one works. There's no good theory that predicts that one. 36. $123.7 joules will raise the temperature of 10 grams of metal from 25 to 60. What's the specific heat capacity of the metal? All right. If you look at the formula, and you're trying to solve for heat capacity is the heat divided by the mass divided by change in temperature. So 123.7 joules divided by how many grams? 10 grams. And then delta T from 25 to 60. So 60 minus 25 degrees C. And the units of measure tell us, we know the units here is supposed to be joules per gram degree. Joules per gram degree. So we know we set it up right. And that should be 0.353. Okay. And that's true of most metals. Most metals have a heat capacity that's less than water. Water is 4.184. Most metals are less than that. All right, 38. On a cold winter day, a steel metal fence. Now, this one takes some imagination. A steel metal fence post feels colder than a wooden fence post of identical size because, okay, if you, I always get this image of Dumb and Dumber. I think it was Dumber that tried to lick the pole and got his tongue stuck. Yeah. Okay, so why does the steel fence post feel colder than the wooden fence post? Well, if we set it up like this, the heat for the steel, and I'm just going to use iron for steel, we know it's got some carbon in there, is equal to Sm delta T. And the Q for the wood equals, well, S M delta T for, these are going to be two different values. And this is wood mass and delta T for the wood. Okay, we got those two situations. It said that they're the same size. Now, I'm assuming since our value for size is mass, that the fence post would have to be the same mass as the steel post. So these would be constant between the two. And why does this one feel colder than that one? Because there's a greater difference in temperature. Well, actually, the temperature is a sensation in your skin when you touch it. So that would mean that more heat would have to be transferred from your skin, and they have to be at the same temperature because they're sitting there in the cold, right? So actually, we can look at this two different ways. We know this one's going to be different than that one, specific heat. How about the Q? Is the Q going to be different? Q transferred would be different, right? So we've got these, this is constant. Let's say the temperature change is the same. Temperature is from whatever the temperature outside is and the temperature of your skin, which is the same. So this is going to be constant. These are going to be constant, right? So if these are constant, if this is a K and this is a K, they're not changing. Then what we've got is, let's solve K equals Q divided by S for both of them. So if that's constant, let's see, is that right? Q divided by S? Yeah. So if the amount of heat transferred is greater, no, that doesn't work. My explanation's falling apart on me already. The temperature change has to be different. Yeah, the Qs are constant. And the temperature change is different because that's what you sense. You feel a difference in temperature. Okay, so this is variable with that. All right, if we put the mass on this side and the mass on this side, now we've got a constant here and a constant here equal to S and T, delta T equals S and delta T. All right. So we know that if this is constant for both of them, then and this one feels colder, that means T has to be, a difference in temperature has to be larger than this one. That means the specific heat has to be less. Specific heat for iron or the steel fence post must be less than this one. Remember, this is like Boyle's law. Constant equals pressure times volume. One goes up, the other goes down. So if we're going from here to here, and we're saying this one has a higher temperature change than this one does. That means that this one must have a lower specific heat than that one. Specific heat of wood must be higher. And the best answer to that one is B. Let's see. 43. Consider the reaction. Okay, we're burning alcohol again. When a 21.1 gram sample of ethyl alcohol is burned, how much energy is released? Okay. So this is a stoichiometry problem with heat as a factor. So if we have what was it? C2H5OH, C2H5OH, that's a liquid, plus 3 oxygens, right? And 2 carbon dioxide and 3 water. Like CO2 and 3 water. Is it going to be a gas? No, it's a liquid. Under standard conditions, it'll be a liquid. All right, so delta H is negative 1.37 times 10 to the third kilojoules. Yes. And you may remember from the video, this value doesn't have to have kilojoules per mole of anything, because this is what happens when that happens. So if you're relative to 1 mole of ethanol being completely consumed in this reaction, it would be that many kilojoules per mole of ethanol. Or it could be that many kilojoules per 3 moles of oxygen, or per 2 moles of CO2, or per 3 moles of water. Either way, any one of those ways work. So that's why we don't put a denominator with this value, because it applies to that balanced equation. Okay, when 21.1 grams of ethyl alcohol is burned in excess oxygen, it doesn't say. We have to assume it's burned in excess oxygen. Otherwise, we can't solve the problem, right? This is the limiting factor. It's going to be all used up. We want to know how much energy is released. All right. So if that is kilojoules per mole of that, then we have to find out how many moles we have. Does it give the molar mass for us? Yeah, 4607 grams per mole. And I write it that way so that the grams will cancel and leave us with moles. And I get 0.458 moles. Now we can convert this. This is moles of ethanol. That's my abbreviation for ethanol. And this is minus 1.37 times 10 to the third kilojoules per mole of ethanol. And I get minus 627 kilojoules. C, 6.27 times 10 to the square. All right. You're on time. I've used up an hour so far. All right, 45. The total volume of hydrogen gas needed to fill the Hindenburg was 2.11 times 10 to the 8th liters at 1 atmosphere and 24.7 degrees. How much energy was evolved when it burned? Okay, so our stoichiometry is hydrogen gas plus half an oxygen gas yields water equals liquid. Okay. And delta H equals negative 286 kilojoules. All right. In order to find out how much energy was evolved, we need to know how many moles of hydrogen were consumed. That's really the question. Because that's the only thing we got to go on is the amount of hydrogen in those bags, in that big dirigible. So if we've got 2.11 times 10 to the 8th liters, and 1 atmosphere pressure, and temperature of 24.7 degrees, can we determine the number of moles of hydrogen? Yep. Ideal gas equation. Okay. So if we do that, that means this one has to be converted to K. So that would be 297.7 K. And PV equals nRT, and number of moles equals PV over RT. Okay. Pressure is 1 atmosphere. Volume is 2.11 times 10 to the 8th liters. That's good because our constant is liter atmospheres per mole K, which is 0.08206. And temperature is 297.7. So that should give us the number of moles of hydrogen. You know, 206 and 297.7. So I get 8.64 times 10 to the 6 moles of hydrogen. Oops. Okay. Went too far with the reaction there. Okay, so now this is how many kilojoules per 1 mole of hydrogen. Okay, so if this is the number of moles of hydrogen, I can multiply that times minus 286 kilojoules per mole of hydrogen. And that cancels the moles of hydrogen and leaves us with kilojoules. And I get, and this is going to be the amount of heat, which is minus 2.47 times 10 to the 9th kilojoules. It's a lot of energy. Yeah. You seen films of the Hindenburg burn? Yeah. See a couple of people running out from underneath it. I wonder if they made it. You know why the Germans had to use hydrogen in their balloons?
Because we wouldn't give them helium.
Exactly right. We embargoed them. They had no choice. Now, the disadvantage to hydrogen, of course, it's flammable. The advantage is it has a greater lifting power because for the same volume, you have half the mass because helium's about 4 and H2 is about 2 atomic mass units. So you get greater lifting power, but you got to be extremely careful. And we don't even know why it blew up. They think it was static electricity. It wasn't properly grounded when it got close to the mooring mast and a spark jumped and boom. Actually, it didn't boom, it burned. 46. Where did our helium come from? You know that?
I don't know.
Well, if it came from the atmosphere, the Germans could get it just as easily as we could. But the atmosphere doesn't have much helium in it. Right. Comes from natural gas. When you clean up natural gas, you take stuff out of it like dirt, water, and other gases. And they extracted the helium from it and saved it, pumped it underground into abandoned salt mines. That's where our strategic reserve of helium was kept. Still is.
Kind of funny, like the Titanic and the Hindenburg, so like the new transportations.
Yeah. Uh-huh. Yeah, that's right. Titanic was unsinkable. Okay, 46. We're going to combine methane and chlorine to make carbon tetrachloride and hydrogen chloride gas. Based on the Breville reaction, what energy change occurs when 1.2 moles of methane reacts? Well, the delta H for this reaction is minus 434 kilojoules. Based on that reaction, that's per mole of methane. So if we know how much methane, 1.2, yeah, 1.2 moles of methane, that's a simple calculation, just 1.2 times that. So if I did my math right, it released, because this is negative, released 5.2 times 10 to the fifth joules. So we don't have to put the sign on it because we're saying whether it's released or absorbed. A small but significant point. All right. How about this one? Specific heats of these metals, if the same amount of heat is added. Oh, okay. This is a logic question, actually. If the same amount of heat is used to heat these metals, 25 grams of each one, and they're all start at the same temperature, which one will end up at the highest temperature? The one that ends up at the highest temperature is the one with the lowest heat capacity. Heat capacity means it can absorb more heat with less temperature change. So the lowest heat capacity will give you the highest temperature at the end, and that's lead. Like 0.127 joules per degree C, per gram degree C. Now you can do that with the formula if you want, but logically speaking, that's what specific heat means. How much heat does it take to raise 1 gram of substance 1 degree Celsius? All right, I'm going to skip these A, B, C's, and D's. I don't care too much for them. Oh, now we're getting to Hess's law. 59. Given the following reactions with their enthalpies, 1, 2, 3, and 4, calculate the delta H for the reaction below. So the reaction below is our target equation. That's what I call it. P4O10, P4O10, solid. Yep. 6PCl5, 6PCl5, and that's a gas. And that yields 10Cl3PO, 10Cl3PO, and that's also a gas. Okay, that's our target equation. So when you're using Hess's law, and you're going to take these individual equations and put them together so that they add up to that one. That's what we want to do. The best thing to do is to go through here and say, all right, I've got P4010. Which one of those has P4010 in it? Looks like Roman numeral 2. So if we use Roman numeral 2 as our first one, P4010 is on the wrong side. Right? There's only 1 mole of it in that equation, and there's 1 mole of it in this equation. So really all we have to do is flip it. So we put P4010 on this side. And that's equal to P4 solid and oxygen 5O2, O2 gas. Now, how about our delta H? If we invert the equation, changes the sign on the delta H. So that would be positive 2967.3. These are all kilojoules, I believe. Okay, so we've used number 2. We've taken care of this one. Now, how about PCl5? PCl5 is number 3, but it's on the wrong side. So if we put PCl5 on this side, and it's PCl3 gas plus chlorine, yeah, plus Cl2 gas. Okay. That means we have to change the sign, but we also need 6 of these, right? So if we multiply 6 times this, 6, 6, we also have to multiply 84.2 times 6. We change the sign to positive 84.2 times 6, and that's 505.2 kilojoules. Okay, takes care of this one. Okay, now Cl3PO. That's number 4, Roman numeral 4. Right? It's already on the side it needs to be. And it's already the exact up, but we need 10 of them. All right, so we don't have to change the sign, but we do have to change, we have to multiply it by 10. So PCl3 on this side, PCl3 plus 1/2 O2. This is before I multiply it. And then Cl3PO gas. Okay, now we got to multiply it by 10. Give us this one. 10 here. 1/2 of 10 is 5. And 10 here. And then we take minus 285.7. Well, minus 285.7 kilojoules. Multiply by 10. Okay, so that takes care of this one, that one. All right, we've got everything we need from this equation, but we've added some extra stuff. We've added these, we've added those, we've added, let's see. Yeah, we've added this one also. So let's see, can the others help us? We got 2, 3, 4. How about 1? 1 has a P4 solid. There it is. So if we put it like it is on this side, P4 solid. And 6 Cl2. And 4 PCl3 gas, 4 PCl3 gas. Now, is that going to take care of the problem for us? Well, that gives us 4 of these, and 6 of those is 10, and there's 10 over here. Yep. That cancels that, that cancels that, that cancels that. So that tells me that we don't have to change anything. Right? Minus 1225.6. Now let's see if the rest of them disappear. Right, 502, 502. Got that. P4, got that one. Okay. And 6Cl2. 6Cl2. All right. Cancel, 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 cancel. This one goes here. Cancel, cancel. This one goes here. That one goes there. Cancel. We're good. So now, once we've got it set up that way, and if we add all those together, it gives us this equation, then we can just add those together and get the enthalpy for this reaction. Let's see. 2967.3. And this is a negative 28. Did I do that one right? Yeah. 2857 and 12256. So I get a negative 610 kilojoules. Is that close to the answer? Yeah, okay. Actually, it's 610.1. I just rounded it off. Like I said before, these types of problems, you have to be extremely methodical. I mean, you can't solve the problem in your head and slap it down on paper. It won't work. For most people. Now, we got any geniuses in here? No, I'm not either. So we have to do it the hard way.
You ever met a genius? Like you ever met somebody who's like crazy?
Not face to face, no. I imagine I probably wouldn't like them. But it does something to your personality, usually. Makes you want to be president or something like that. Makes you want to have power over people because they're lesser than you are. Einstein had trouble with math. I think his problem was he was bored. But he had a very vivid imagination. And when he needed to, later on, when he needed to publish any of his ideas, and he needed to work out the math to prove his thesis, he went to people who were good at math, got them to help him. He didn't do it all by himself.
He just thought of the theories, got other people to prove them.
He worked on the math himself, he worked at it, but he wasn't always successful. And he had places, roadblocks, stumbling blocks. He couldn't get around it. So he'd call on people like, I don't know, Schrodinger or Heisenberg or some of the other big names and have them help him. I think de Broglie was active then too. But he spent a lot of time just thinking things. He was famous for thought problems. Like relativity, he thought of, what would happen if somebody were, I'm observing, but there's somebody inside that elevator falling at a constant velocity. And they've got a clock in there and I've got a clock out here. Then he said, all right, what would happen? Stuff like that. Okay. 68. And young physicists have been trying to shoot down his theories for ever since, make a name for themselves. In fact, later in life, he was asked, why do you spend so much time on this unification theory? Trying to take all the fundamental forces of the universe and combine them into one theory, like gravity, electromagnetism, strong nuclear force, weak nuclear force, put them all together, right? He says, because I can afford to. I've already made my name. I'm old and I can spend my time doing what I want. These young guys, they have to produce. And once they produce, then they can spend their time thinking about stuff that doesn't matter. Okay, 68. Choose the correct equation for the standard enthalpy of formation of carbon monoxide gas. And it gives you the heat of formation. All right, when you're asked or when you need to generate a standard enthalpy of formation equation, you start with the product. 1 mole of the product, CO. And from this point on, you don't touch that side. This side has the elements in their standard, most stable standard conditions. So we need carbon. Carbon's most stable form at room temperature and pressure is graphite. Right? We got 1 mole here, 1 mole there. We're good. Oxygen, however, is most stable at room temperature and pressure at O2. Right? It's one of our diatomic elements. So we need half of that one. That's the equation for the standard heat of formation. And then, of course, we're given the delta H zero for formation at minus 110.5 kilojoules. That's it. So whichever one matches that, C. Anytime you have to write a standard enthalpy equation, enthalpy of formation equation, that's the way you do it. Let's see, 78. We're doing on time. Let's see, we're supposed to start lab at 3:35. Okay. I think we can finish. I stopped telling stories. One of the main advantages of hydrogen as a fuel is that what?
So it combusts easily, and it like has, I don't know, whenever it ignites, it has a bigger low pressure.
Okay. You're saying it has more energy per unit, whatever?
Yeah.
Yeah, that's a tricky thing. That's an engineering problem.
I'm
No.
not saying like if you use hydrogen instead of gasoline, it's going to create it's going to create more energy. It's going to push the piston down faster. And it explodes.
Okay. The problem with that is gasoline's a liquid and hydrogen's a gas. Now, of course, gasoline, when you spray it into your cylinder, it converts to a gas. But each molecule of essentially octane is that, and that's hydrogen. So if you burn them, see, yeah, if you burn them, this one gives you only water, nothing else. This one gives you carbon dioxide plus water. Now that's not balanced, of course. The advantage to using hydrogen is when you burn it, you only get water. That's it. Okay. Now, as far as a rocket fuel goes, they use hydrogen in rockets as a liquid. And it has to be converted into a gas, of course, and mixed with oxygen before you can use it. But it has a very, very high specific impulse, we call it. That is, it gives you more push for the same number of moles. I think that's what you were getting at.
Yeah, that's what I'm saying.
Right. So, but to get it off the ground, specific impulse is not where it's at. To get it off the ground, raw brute force gets it off the ground. Like see, what does Musk call his booster? I know a Starship sitting on top.
Engine. I think it's called the Raptor.
Well, the Raptor engine, yes. They're starting to use the Raptor 3 now. But the whole booster, the bottom part of the rocket is like, what is it, 14 or 15 million pounds of thrust out of those 33 engines. That's what gets it off the ground. Once you get into space, then specific impulse becomes more important because you're not fighting that surface gravity anymore. Okay, so the answer is the only product of hydrogen combustion is water. That's the main advantage of hydrogen. Now, there are other advantages, of course, but that's the main one from an environmental standpoint. And you don't have to just burn it. Right? You can run it through a fuel cell and get electricity directly. In fact, that's what they used on the Apollo missions to the moon, fuel cells. So they had a hydrogen tank and they had an oxygen tank for breathing air. Plus they used some of that oxygen in the fuel cell to power the spacecraft. And I think it was the oxygen tank that blew up on Apollo 13.
One with like the teachers and stuff.
No, Apollo 13 was before that. Yeah, you're talking about Krista McAuliffe.
Yeah, all the people that died.
Yeah, that was, let's see, which one of the shuttles was that? Columbia? I think it was Columbia. Or Challenger?
Got a challenge.
Challenger was first, wasn't it? Then Columbia burned up on re-entry. That's right. Yep, they tried to launch that thing when the weather was too cold. And the O-rings couldn't hold the pressure in the solid rocket boosters. They burned through the O-rings and then they burned into that orange tank. And that's all she wrote. 79. Which of the following is not being considered as an energy source for the future? Well, ethanol is already being produced as a product of corn. By the way, it takes more energy to make a gallon of ethanol from corn than it does just to burn the corn. So if it wasn't for government subsidies, the corn to ethanol industry would disappear overnight. The economics aren't tenable. Methanol, some countries are experimenting with methanol as a product of biomass conversion. Seed oil, that's another possibility. In fact, diesel engines were created originally to run on vegetable oil. Shale oil, right? As long as we can get back to fracking, we'll get all the shale oil and natural gas we can handle. In fact, at the end of Donald Trump's presidency, the first time around, we were a net exporter of energy. You know, if they'd have kept his policies in place, we could have kept Europe out of hot water with Russia, with their natural gas. They held them hostage with that.
So what was everybody's problem cracking?
They claimed that it contaminated aquifers because you're pumping a mixture of water and mud and oil and some other stuff down there under high pressure in order to crack the rock and release the contents. That was debunked. And when it comes back to the surface, of course, because you got to bring it back out so you can get the gas and the oil out behind it. What do you do with that stuff? You know, that's another waste product. But the industry has matured, and the waste is much, much smaller than it used to be. Well, to answer the question, you can't consider carbon dioxide as an energy source because it's a product of energy. Right? Carbon dioxide, if you look at, let's see, we've done oxidation states, haven't we? Yeah. So if you have methane in Elon Musk's rocket, hydrogen is a +1 oxidation state, so that's a total of +4. That means this has to be a -4. CO2, oxygen is -2, so it's a -4 total. That carbon is a +4. It goes from -4 to +4. That's a transfer of 8 electrons for every carbon. So if you release 8 electrons from this carbon, they go somewhere else and leave behind this oxidation state. This is the high energy, this is the low energy. So carbon dioxide is the lowest possible energy for carbon. It's no good as a fuel.
Unless it's for like a tree or something.
Oh, it's food for a tree. Yeah, right. Yeah, they suck carbon dioxide out of the air and fix the energy from sunlight. Yeah. That's right. So we need more CO2 in the atmosphere, make our plants more productive. In fact, that's been proven in the field and in the greenhouse experiments. You increase the CO2 concentration in your greenhouse or your growth chamber experiment with plants, and their productivity just goes through the roof because they've got more food. All they need is sunlight and water. And the reason we've got oil and coal beds, feet thick, is because at one time in the Earth's history, it was overproducing. It had very high carbon dioxide levels in the atmosphere, and the plants were just going wild. They were creating more biomass than the ecosystem could handle. So they died and they fell and got covered in soil and compressed. That's where we get our coal. If you go to a coal operation and you see the tailings, you can pick up a piece of either coal or the rock that comes out with it, and you can find imprints of plant leaves in there. What used to be plants. Okay, we're getting close. Let's see what this one is. Number 90. Actually, if you look at if you make a demographic comparison of death rates during cold snaps and hot snaps, so to speak, you'll find that more people die from cold than they do from heat. Okay, number 90. A gas absorbs 188 joules of heat. A gas absorbs 188 joules of heat. So if the gas absorbs that much heat, that means we're adding the heat to the gas, right? And the gas does how much work on its surroundings?
310 joules.
310 joules. That's going to be negative, right? So that's 132. Negative 132 joules of work is done on the surroundings. Oops, I made a mistake. Is it 2? Let's see. 10, 11. Yeah. Calculation error. So negative 122 joules is the internal energy of the gas, the change in internal energy. That's all I did. I just added those two together, keeping the signs, and we ended up with a negative 122. All right, let's see. I got a few more minutes. Hope I can get them all done, but we'll try. All right. Nitric acid. This is all fluff. Nitric acid was prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3. calculate the delta H reaction for this reaction. All right, we've got 1 mole of each. 1 mole of saltpeter, 1 mole of sulfuric acid yields 1 mole of sodium bisulfate and 1 mole of HNO3. So in order to find out the delta H for these, if we have the formation heats for each one, all we need to do, let's see, this is 99. All we need to do to find the delta H of reaction for this one is we sum up all of the heats of formation of the products and subtract, that's what that sigma means, summation. Subtract the heats of formation for the reactants. Okay? And since they're all 1 mole, we multiply them all by 1. Right? If you have a heat of formation, of course, is based upon 1 mole of the compound. So if you have, in your equation, if you have more than 1 mole, you have to multiply that times the value. Okay, in this case, we don't. Sodium bisulfate is minus 1125.5 kilojoules, right? And then nitric acid, HNO3, is minus 135.1. Okay, then we subtract the reactants. Sodium nitrate is minus 467.8. Oops. 0.8. And then, well, the next one's a minus also. Sulfuric acid, which is minus 814. Minus 814. Okay, so whatever minus we get over here becomes positive. And if we do our math correctly, we should get 21.2 kilojoules. Positive. 21.2 kilojoules for that reaction. That's why they say heating sodium nitrate with sulfuric acid. It's an endothermic reaction. We have to put energy in to make it work. Oh, that's it.